What is up? What is up, everyone? Welcome back to Nick Does Maths. It's maths. I'm fairly sure it's maths. We're in the world of stats today. Hardcore stats. We're going to talk about bias in estimators. What do we got? We have a huge bag of marbles. Like all good mathematicians, we just have bags and bags of marbles. Like the one pictured here. Bing! In this bag, there is a proportion P of yellow marbles. Of course there is. We want to figure out what P is. To do that, we take 3 samples of size N, and we measure the number of yellow marbles in each of those samples. Now, every time I do this, I will get a different number of yellow marbles. It's like I'm doing it blind. Okay, so these are random variables. Y1, Y2, Y3 are the number of yellow marbles in my 3 samples. They are random. I don't know what they're going to be. Now I have 2 ideas. These are going to be my first estimator for the proportion of for the proportion of yellows in there is, for whatever reason, because I on the whim this day, I decide I'm going to take the number of yellow marbles in the first sample, 3 times the number in the second sample, twice the number of yellow marbles in the third sample, add, subtract them in this way, and divide by 2n. Sure, why not? You go nuts. And another idea is my friend comes along, Neil, and he says, well, work acquaintance, he comes along and says, no, Nick, you're being silly. Instead, we're going to twice y1, 3y2, y3, add them all up, divide by 6n. Okay. First thing we're going to do is we're going to show that P1 hat and P2 hat are unbiased estimators. Now, what does that mean? In fact, these are not completely unreasonable estimators. Why is that? Well, what we want to show is that the expected value of P1, right? So every time I take my 3 samples, these are random, so this is random, I will get a different value of P1 hat and a different value of P2 hat, right? And so on. I'll generate 100 times, 200 times. But what I would quite like is for that on average, that number on average, this random number on average, the expected value of it will in fact give me P. That is what I want. That is what I'm looking for a good estimator, or for an unbiased estimator. So the expected value of P1 hat is, using the rules of expectations, that is the expected value of y1 plus 3 times the expected value of y2 minus 2 times the expected value of y3 over 2n. Now let's talk about these 3 things. Each one of these is a sample of size n. Now, the fact is that this bag has lots and lots of marbles. The idea there is that by removing one yellow marble or a non-yellow marble, we aren't affecting the probability of pulling out the next yellow marble. That's the significance of it being a huge bag of yellow marbles. So what this means is these follow a binomial with n marbles in that sample, each marble a probability p of being yellow. So what that means is, being the smart people that we are, we know that the expected value of y1 is the same as the expected value of y2, is the same as the expected value of y3. That is just np. So that tells me that the expected value of p1 hat is np, 3np minus 2np over 2n, and that is in fact, dun da da da, red pen of cancellation. Oh no, the P's good, the P can stay, it's the N that needed to go. I'm sorry P, you can stay. That gives me 2P over 2, which is P. So in fact, I wasn't insane at all. That seems like a completely reasonable estimator. On average, if I do this calculation, I will end up with P. Ha! Suck it. Now, what about Neil? P2. Well, using the same idea, that will be 2np plus 3np plus np over 6n, which does in fact give me P. So it is also an unbiased estimator. is also unbiased. Oh, that is just smudges all. Stop it. Stop it. Unbiased. Cool. Which one do I use? Because obviously it's important to know which one is best. Well, let's find the variance of P1. Let's find the variance of P1. Well, the variance of P1 is, again, now y1, y2, and y3 are independent. So I can say that the variance of P1 is the variance of y1 plus 3 times the variance of y2 plus 2 times the variance of y3 over squared over 4n squared. What are we using on this one? We are using the fact, if we remember correctly, that the variance of ax is a squared var of x. That is the 2-1. Okay. And of course, the variance of any one of these things, so that would be 1, 10, that is 14. The variance of these things is n p 1 minus p. So these are all identical. So I've got 1, 9, 4, 14 on top. Whoops. Over 4n squared. So that is 7 p 1 minus p over 2n. Okay. Now we are told that the variance of P2 is 7 p 1 minus p over 18n. Is that correct? Still be 14 on top, but it'll be 36. Yeah. Now why does that tell me which one is better? So both of these estimators, both of them, on average, will give me p. All right? But I'm not going to take an average. I'm going to take one sample. I'm going to take one lot of this, right? So what do I want? So yes, if I take lots of P1s and lots of P2s, on average, they both come out as P. But what about an individual value? So whilst their mean is at P, what I'd quite like is that these individual things stay quite close to P, i.e. what I want is I want the one with the smallest variance. The smallest variance, the smaller deviation between your individual measurements of P1 and P2. All right? So between P1 and P2, I want to choose the one that has the smallest variance. Okay? Because that means whilst they both average out at P, my individual values will be closer to P for the one with the smallest variance. That's what the variance measures. So which one has a smaller variance? P1, 7p1 minus p over 2n, or P2 with 7p1 minus p over 18n? It's P2. P2 is the better estimator. Yup. Yup. Cool. We're not done. Let's go to the next part of this question, which we are going to get into right now. Yes, right. It worked. I wasn't sure I still had that power. We're going to add in a third estimator, P3. y1, ay2, 3y3 over bn. We want to find a and b positive integers so that P3 is in fact the best estimator between the three. Well, what do I need? Well, first of all, I need to find a and b so that it is unbiased. So its expected value is p. So that will be the expected value of y1, which is np, plus a lots the expected value of y2, plus 3 lots of the expected value of y3 over bn. That's got to equal to p. So what's that? That is 4 plus a lots of np over bn has to equal to p. So that tells me that b has to equal to 4 plus a. All right. So let's find the variance of my P3. The variance of my P3 will be the variance of Y1, NP1 minus P, plus A squared, NP1 minus P, plus 9, variance of Y3, NP1 minus P, over B squared, N squared. Right. Well, one of the n's cancels out, which is quite nice. So what do I need? So this is 10 plus a squared p 1 minus p over b squared n. That has to be less than, well, already my best variance is here. So if I want this to be an even better estimate, that has to be less than this. So that is less than 7p1 minus p over 18n. Now, I can divide through by that and that. That's all positive, no dramas. N is positive, no dramas. So what do we need? We need 18 times 10 plus a squared has to be less than 7b squared, but b, remember, is 4 plus a. Okay, so if we expand that, 18a squared minus 7a squared, that is 11a squared. We might need the calc for this, I won't lie. 8 times 7, we're going to get 56 a's from there. And then 180 minus 7 times 16 is 68. That's got to be less than 0. Does this do anything nice? Ain't no one got time right now. So this tells me that A has to be between 2 and 34 over 11. Right. Now, if A is equal to 2, now this is strict inequality. Why? Well, because if it was equal to, I can just take P2. If it was equal to, I can just take P2. And in fact, yeah, I'm not sure what that would give. I would take A is 2, B is 6, and we go from there. All right? And we'd end up with the same numbers as P2. But there is a better one. There is a better one. All right? So I want this to be negative. We're going to take A. What value of A is in between these two? We're going to take A as 3, and therefore B is 7. A is 3, and therefore B is 7. And that one's even better or gooder. Whew, that was fun. Could we do better? What do we think is the best combination, really, fundamentally? Right? All three of these are unbiased estimators in increasing order of goodness of fit, because they are the variance decreases for each one. What should we do as a linear combination of y1, y2, and y3 for this to be minimal? What do we think? What do we think? All right. So at the moment, this would give me a variance of, are any of these better than our bog standard one? So that will be 9, 18. That will be 19p1 minus p over 49n, I do believe. P2, 2, 3, oh, and 1. There we go. Sorry, I miswrote that one. Because then 7, 7. Yep, okay, fine. Let's go with that. Now, how about we investigate very, very quickly the one that probably makes more sense for me, which is, why don't we just average the 3? Why don't we just average the 3? What will that do for my var? That will give me 3p1 minus p over 9n. So which one is better? That is even smaller than that one. All right, that would be even smaller than that one. I'm fairly sure. (19/49). Yeah. Yep. That is our best one. Can we prove it? One for you to try at home. See what you can do. Is that our best one? Can we come up with a better estimator using combinations of y1, y2, and y3? Can we come up with one that has an even smaller variance than that? Don't know. Have a think. In the meantime, I'm going to check out for today. Hope you enjoyed it. If you did, if you didn't, if you just want to support the channel, please subscribe. Please give us a like. Love me some likes. Even say I like a like. Hit the bell for notifications and tune in next time. I'm Nick. This was Maths.